Now, let's move on to the second law of thermodynamics. Statement: it cannot spontaneously flow from a colder body to a hotter body without external work. Explanation: natural heat flow means heat always flows from hot to cold, not the other way around. Example: if you keep an ice cube in a warm room, heat flows from the room hot body into the ice cube cold. No spontaneous reverse flow. It means heat will not move on its own from the ice cube into the room. This is against nature's direction of heat transfer. External work needed. If we want heat to flow from cold to hot, we must supply external energy and work. Example: a refrigerator pumps heat from inside means cold space to outside means hot room by using electric power. The law explains the direction of heat flow in nature. Heat transfer from cold to hot is possible only with external work. In simple words, heat naturally flows from hot to cold, never cold to hot, unless we force it by doing work. Equivalent statements of the second law of thermodynamics. Kelvin-Planck statement: no heat engine can be 100% efficient. It means a heat engine converts heat energy into work. According to this law, some portion of the heat observed from the source must be rejected to the sink. That means it is impossible to convert all the observed heat into useful work. Example: in car engines or steam engines, part of the heat is always wasted as exhaust gases are lost to the surroundings. Next, Clausius statement: heat cannot flow from a colder body to a hot body without external work. It means heat naturally flows from hot body to cold body. For heat to move from cold body to hot body, we must do external work. Example: a refrigerator or air conditioner uses electricity means external work to transfer heat from the cold inside to the warmer outside. Next, applications of the second law of thermodynamics. Let's explain each one clearly, point to point. First one, heat transfer. It means heat always flows from hot to cold naturally. Example, a hot cup of tea cools down when left in a room because it transferred to the cooler surroundings. The second law explains the direction of this heat flow. Second one, refrigerators. A refrigerator removes heat from cold space and rejects it to the warmer surroundings. This is possible only by doing external work. This directly applies the Clausius statement of the second law. Third one, engines. It means heat engines like car engines, steam turbines convert heat into work. According to the second law, no engine is 100% efficient. Some heat must always be rejected to the surroundings. This is based on the Kelvin-Planck's statement. Fourth one, melting of ice. Ice melts when heat flows from the surroundings into the ice. This happens spontaneously, but the reverse process cannot happen on its own. This shows the natural irreversibility explained by the second law. Fifth one, mixing of gases. It means when two different gases are kept together, they spontaneously mix. They never separate on their own into pure gases without doing external work. This is another example of natural process being irreversible. The final explanation. The second law explains heat flows in a fixed direction. Refrigerators need external work. Engines cannot be perfectly efficient. Melting and mixing are spontaneous and irreversible processes. The image illustrates the concept of entropy and its relation to heat transfer and the second law of thermodynamics. The image shows heat transfer means heat delta Q naturally flows from a region of higher temperature T1 means hot to a region of lower temperature means T2 cold. This spontaneous flow is a fundamental aspect of the second law of thermodynamics. Entropy means entropy delta S is defined by the equation delta S that equals to delta Q by T. It represents the measure of disorder or randomness in a system. Second law of thermodynamics. This law states that for any naturally occurring process, the total entropy of an isolated system or the universe will always increase or remain constant. It will never decrease. The heat transfer from hot to cold, as shown in the image, is a spontaneous process that leads to an increase in the overall entropy of the system. Now, let's move on to the third law of thermodynamics. Statement: as the temperature approaches absolute zero, the entropy of a perfect crystal approaches zero. Explanation: absolute zero means 0 Kelvin, that equals to minus 273.15 degrees centigrade. This is the lowest possible temperature. At this point, molecular motion is almost completely stopped. A perfect crystal means a solid material with no defects in its arrangement of atoms. All atoms are arranged in a perfectly ordered structure. Entropy meaning measure of disorder or randomness in a system. Higher entropy means more disorder. Lower entropy means more order. At absolute zero, it means in a perfect crystal, atoms are fixed in perfect order. Hence, this order equals to zero means entropy equals to zero. Entropy of a perfect crystal at absolute zero, that equals to zero. No system can have negative entropy. Example: imagine ice crystals forming at very low temperature. As temperature decreases, molecules vibrate less and arrange more neatly. At 0 Kelvin, perfect arrangement means zero entropy. In simple words, as temperature reaches absolute zero, a perfect crystal becomes perfectly ordered. So, its entropy becomes zero. Next, applications of the third law of thermodynamics. First one, determination of absolute entropy. This means the third law allows us to calculate the absolute entropy of substances by measuring heat capacities down to near absolute zero. This helps in studying chemical reactions, phase changes, and thermodynamic properties. Second one, prediction of chemical equilibria. Using absolute entropy values, we can calculate Gibbs free energy means delta G. This helps in predicting whether a chemical reaction will be spontaneous or not. Third one, low temperature physics means cryogenics. Cryogenics means study of materials and systems at extremely low temperatures. The third law helps understand how gases liquefy like oxygen, nitrogen, helium when cooled near absolute zero. Fourth one, attainment of very low temperatures. The third law shows that absolute zero cannot be reached, but we can approach it using techniques like magnetic cooling. This is important in research on superconductors and quantum systems. Fifth one, material science. This means properties of metals like electrical resistance, magnetism, and thermal expansion change at low temperatures. The third law helps scientists design superconductors, semiconductors, and magnetic materials. Sixth one, 0 point energy concept. This means even at absolute zero, atoms still have a very tiny energy left called 0 point energy. This concept is important in quantum mechanics and explains why particles never completely stop moving. The image illustrates the third law of thermodynamics, which states that The entropy of a perfect crystalline substance approaches zero as the absolute temperature approaches absolute zero, means 0 Kelvin. S equals to 0 as T equals to 0 Kelvin. This mathematical expression shown in the image represents the core of the third law. Here, S denotes entropy and T denotes temperature in Kelvin. It signifies that as the temperature of a system approaches absolute zero, its entropy also approaches zero. Perfect crystalline substance means the image depicts a perfect crystalline lattice structure, which is crucial for understanding the third law. A perfect crystal at absolute zero would have a highly ordered, unique ground state, meaning there is only one way to arrange its components, leading to zero entropy. Entropy and disorder means entropy is a measure of disorder or randomness in a system. At absolute zero, a perfect crystal has minimal thermal motion and a highly ordered arrangement of its constituent particles, resulting in the lowest possible entropy. Impossibility of absolute zero. It means while the third law states that entropy approaches zero at 0 Kelvin, it also implies that it is practically impossible to reach absolute zero in a finite number of steps. Thank you very much for taking the time to watch this video. Padmam Himam.